Okay, so this is a special science session here at US CLIVAR across panels on big data and machine learning for climate science. It's an exciting topic. There's a new working group, and that's actually the first talk of this session is by Mike Pritchard from my institute, UC Irvine, and he's going to introduce the new working group about emerging data science tools relevant to CLIVAR.
Great. Hey, CLIVAR. Thanks for having us. I've got 10 minutes here, but I want to just tell you about this new working group and our three main themes here about modeling and data-driven discovery and mostly talking to each other, and then let you know what's coming down the pike. But let's dive in. So this is a team effort. I want to acknowledge co-lead Libby Barnes and other co-leads Amy Braverman at NASA JPL and Pierre Gentine. So this is very much jointly conceived idea. And basically, CLIVAR is concerned with modeling of observations and analyzing observations, right? So, but both of those issues are facing an issue with exploding information and complexity of the tools associated with that information. And that's really sets the stage for this working group because we're aware of the zeitgeist out there. There are fascinating new tools emerging. We're not alone in our field with this issue of big data. New tools to meet these challenges. Here's an example of a deep neural network, which are proving to be surprisingly skillful emulators of high-dimensional nonlinear functions. And you can see evidence of that around you. So neural networks are powering kind of amazing breakthroughs in historically difficult areas of machine learning, like near human level image recognition and superhuman strategic game playing. So anyway, all this means is that, behind these new tools are new algorithms and methodologies. So that's what our team means by data science, these algorithms and methodologies. So you wonder, do these new tools mean we could do new science? Discover relationships that have gone unnoticed, hiding in the correlations that are hard to see, but these neural networks might be able to see. Could we emulate physical models? That's how I got into this. So the main goal here is really just to foster some more understanding and development and adoption of these new tools in ways that hopefully advance the scientific discussions. So to that end, we'll try to unite Earth system science experts with computer scientists and especially statisticians. So we've loosely organized this under three themes. One that I'm most familiar with has to do with how should we change modeling practices. So some things we try to model, like the terrestrial biosphere, are really weak in physical constraints, but rich in data constraints, and so it's an interesting target. Other things like the atmosphere, we have Navier-Stokes, are becoming more and more data rich in higher quality synthetic data. Here's an example of a global cloud resolving model simulation, and of course, large eddy simulations are even more trustworthy synthetic representations of the atmosphere, but large data sets. Okay, so I mentioned I got into this from this physical model emulation angle. So, I've been wondering whether we can take cloud resolving models that live inside of a global climate model and emulate them with neural networks. And I didn't think so at first, but I've been surprised the last couple of years that, yes, surprisingly, these dumb sheets of neurons can prove remarkably skillful at emulating even the PDEs of cloud resolving calculations. So maybe. But there's lots of questions here about that. So there's a glimmer of recent success, but lots of challenges: interpretability and physical constraints and stability and generalizability. And how should we incorporate uncertainties? What are the trade-offs? And especially uncertainties, right? We need to talk to statisticians about this sort of stuff. So the other theme is data-driven discovery. There's huge amounts of observational data out there. We're familiar with using exotic statistical tools to try to make sense of it, like EOFs. But the tools are exponentiating, and some of them are really intriguing. Here's a slide I ripped from Micah Sonneval, who sort of used some of these modern algorithms for clustering to transcend the usual limitations of k-means and arrive at a nice, scientifically satisfying summary of geographic regimes of marine ecosystems. And then here's another example. This is causal inference theory. So it seems there's a mini revolution going on in causal inference, but the idea that we might be able to use some of these tools to identify nodes where information flows to other nodes in the climate system and quantify relationships, either to test hypotheses and quantify relationships that we already have, or hopefully to uncover new processes and covariation. And I think Libby will tell us more about this, but there's a zeitgeist that neural networks are black boxes, and that's changing. We expect computer science to help us understand which parts of a neural network are yield its skill. So here's an example of a relevance propagation diagram. So there's lots of opportunities. I'll just to say machine learning interpretability could be exciting for climate applications. Promising avenues include things like opening the black box through these tools like input analysis. And there's big questions about how to do this sort of thing for extreme events when the training data becomes smaller. And again, this lingering issue of how should uncertainties be incorporated in this sort of thing. And so that motivates the third sub-theme here, which is that we need flexibility and scope in a working group like this, which is kind of intentionally breaking tradition with this historical CLIVAR working group of focusing on rather than a process, these tools. And we're in the infancy of adopting these tools. So some of us are tinkering, scattered across disciplines, but we need to understand which tools are reproducibly helpful and actually gaining consensus and are also technically approachable. And how should the community organize itself, therefore? And also this working group. So we'd like to, a big theme of this working group is going to be to distill conversations across people and act accordingly. So again, the conversations are needed across these disciplines. So what's coming up? Basically, we're just spinning up. And yesterday, the first invitations went out. We're pleased with the response rate so far. But the goal are bi-monthly webinars, so hopefully something the whole community can plug into if you're interested in following this. That'll start this fall with the idea of having discussions across this community and curating our experiences and curating our tools and our how-to guides. So we're hoping that will all become accessible through an online presence that people can plug into. And then the working group itself will be discussing with each other, especially in years 2 and 3. Also curating experiences and tools with the aim of publishing a couple of papers synthesizing these discussions. Okay, so that's it. Thanks. Email me if you'd like to be kept abreast of it. And we just launched a Twitter account for it too, if you'd prefer to follow that. But thanks for your time and look forward to talking to some of you.
Just real quick, Mike, are there plans to have a community workshop within the working group?
I'm still spinning up on semantics of CLIVAR meeting categories, but we want to meet as a community in various fora, as well as in a working group. Yeah. But the webinars are going to be our main high frequency mode of conversation, and we want those to be totally open. Did I answer your question? Or? Okay, thanks.
Mike, speaker in this session is Earth System Modeling 2.0 towards accurate and actionable climate predictions with quantified uncertainties. He's leading a unique effort at Caltech, and that's what he'll be talking about.
Thank you, Gudrun. Thanks for having me. And a special thanks to Mike and Libby for taking on this working group. I'm really excited to see what's coming out. So I'll talk. Oh, seem to have sent a different title, but same talk anyway. I'm going to talk a bit about what we are doing with some aspects of what you can call machine learning, but it's really closer to data assimilation. And we, as a group of people, scientists at various institutions that is now called the Climate Modeling Alliance, CLIMA. Okay, let's see. There we go. Okay, so that's us. As of a few weeks ago, we are a group of people at Caltech, at MIT, the Naval Postgraduate School, JPL. And what we're doing is building a new climate model. And I'll tell you what's new about the new climate model. It in many ways is recognizable as a climate model, having dynamical cores and the like. It's built to run on modern computing hardware. In fact, from what I know, it may well be the first global model that already runs on GPUs. And I think what's special about this group is, without going through who everyone is, these are applied mathematicians, computer scientists, software engineers, atmospheric scientists, oceanographers, biogeochemists. And at Caltech, we're all sitting in one office space together, which is really a qualitative change for all of us in how we work. And it's really increasing efficiency in transferring knowledge. We are funded by one grant from the National Science Foundation, a software institute, and several grants by private funders, primarily Eric and Wendy Schmidt, and a number of others who are contributing substantial amounts of funding. The total amount of funding, to give you a sense of a scale, it's something 35 to 40 positions in this effort. So let me tell you a bit about what we do and why we do it. So if you look at current models, well, what we want to do is predict global warming. Earth has warmed, as you all know. This is temperature change since the mid-19th century to now. And if you ask how climate will change, you know that, but I think it's perhaps still helpful to put it in terms that are intuitive and maybe you haven't seen. There are various questions you can ask about the climate system. Ultimately, you care about impacts. All impacts in some fashion scale with temperature. And you can, for example, ask how much CO2 can you put into the atmosphere before you cross the 2-degree warming threshold of the Paris Agreement. And here is the CMIP5 models, 29 of them, what answer they give to that question. So we had about 1 degree of warming, 1 more to go before we have 2 degrees above pre-industrial levels. And in some models, you reach this 2-degree warming threshold at 480 parts per million CO2 in the atmosphere. So we have 415. That's something you reach in the late 2030s. And in some other models, you reach this 2-degree warming threshold that goes to 600 parts per million. And the models here are ordered in order of increasing equilibrium climate sensitivity. And what you see is that, of course, the more sensitive a model is, the sooner you cross the 2-degree warming threshold. This is under an RCP 8.5 scenario. It doesn't matter much which scenario you look at to get these numbers, as long as you reach high enough CO2 concentrations. So the uncertainty here is a full human generation. I mean, 600 ppm you're not going to reach before the 2060s. And if those models were right, then climate change would perhaps be something to worry about, but not the biggest threat. On the other hand, if the more sensitive models are right, then of course climate change is a much bigger problem. We'll reach 2 degrees warming within 10, 15 years. And we just fundamentally don't know which one of those is right, if any. And the key difference between the models is that the models on the right that are more sensitive tend to produce fewer low clouds as the climate warms. And the models on the left that are less sensitive tend to produce more low clouds as the climate warms, reflecting more sunlight, mitigating some warming. Of course, there are other differences, but the difference in low clouds accounts for more than half the variance in these predictions. The low clouds, it's stratocumulus off the coast here, pretty much there year-round, or cumulus around the Hawaiian Islands. And we simply just don't know if you get more or less stratocumulus, more or less cumulus as the climate warms. That's just one example of uncertainties in models, but it's the biggest physical uncertainty in models. And of course, all these uncertainties come from small-scale processes such as clouds, which we cannot resolve computationally. And you sometimes hear statements, we just need $1 billion to build a bigger computer and all the problems will go away. Well, no, you need resolutions of order tens of meters at least to resolve these clouds. For that, you need a computer that's billions of times faster than the fastest we have, and no amount of money will buy you that. So we have to be smart instead of just compute yourself out of that problem. And a lot of what I say applies to, say, ocean turbulence in much of the same way as the clouds is something that I've been working on as one example. So what you could do if you had better predictions, well, people have tried to estimate the value of better predictions for society. Better planning of rainwater management infrastructure, how high is seawall to build, and the like. The numbers people come up with is that the value of better prediction lies in the trillions of dollars. And this comes from a paper, it's a few years old, but now you see actually portfolio risk assessment companies take this seriously. They try to value risks and come up with similar numbers. The point is there's huge societal benefit. But I was talking with Jim Todd over the coffee break, and this is what you use as motivation, and that's part of why we do it, obviously. But to actually realize better predictions, there's a lot of interesting science to be done, and it's not just the value of predictions that drives everything. And let me talk about the science a bit. So, clouds, I mentioned that the reason we can't do them is because they're so small scale. There's no way that we'll resolve the low clouds anytime soon, not in the next 50 years, even if Moore's law remains valid and computer power increases exponentially. So you need better process models, and there are various approaches you could take. Mike has been looking at machine learning approaches, and I'll show you what we do more generally for small-scale processes. That's a bit different. The state of the art is that if you look at climate models right now, and say look at low clouds, that's just the one example I use throughout the talk as an example, but take it as an example for several other processes that have similar issues. Black are observations. These are satellite observations of cloud cover, in this case off the coast of Peru, but you could make similar plots off the coast of California here. So you have something like 70% cloud cover in the eastern portions of subtropical ocean basins year-round. And climate models are in color here, the models that have this information. And you'll see, this is from a paper by Lin et al., where the reference is cut off there. And you see that all climate models underestimate low cloud cover severely by a factor 2 or 3. Long-standing, well-known bias. The models produce too few low clouds. They're somewhat artificially made brighter than they would be otherwise. That mitigates some of the energy flux biases, and you get what's known as a too few, too bright bias, which leads to biases in surface temperatures underneath. For example, the SST have generally a warm bias in those regions. Part of it may have to do with upwelling the ocean. A large part, for sure, has to do with the cloud biases. So that's the state of the affairs that has been like that for a long time, for decades, and the biases have been known for a long time. There's nothing new about this. And, well, one reaction is you can throw up your arms and be depressed about biases that have been around for 20 years, but maybe the more fruitful way is, well, look, we have data, we can measure what these biases are, and we can use the discrepancy that you see between models and data here, use it to make the models better. And what we want is, you're building a model that, where the idea is that the model will learn directly from data, from space-based data, from Argo floats in the ocean, but also from data generated computationally. And I just want to show you quickly how we are doing this. So we have global observations, massive amounts of it, and they have not been used to the extent they can in climate modeling. They've been used for climate model evaluation, but very little in the development process of a climate model. So we want to build a model that learns directly from global observations, from space, from floats in the ocean, and the like. Ground-based measurements, say for the land surfaces, it's something the JPL group is working on. And the other capabilities we have is doing high-resolution simulations. So we know the equations of motion for clouds or ocean turbulence. We can solve them. That's not on the globe. On the globe, you would need this computer billions of times faster that we're not going to get, but we can solve the equations in small domains. And you can use information that you get from these high-resolution simulations, likewise, to train a global model, to train process models in a global model. So data we have, one example, space-based data, but float, ground-based data, the same applies. The potential of the data hasn't been tapped to the degree it can. And high-resolution simulations, again, an example of clouds from simulations we have done a few years ago. These are precipitating cumulus clouds in the Caribbean. These are good simulations. They not only look good. Hey, this is modeled after the RICO campaign. You can compare it with field data and actually verify that these are good simulations. The problem is you can only do them in boxes that are maybe 10 kilometers on the side or so, not much bigger than that. But then you get good simulations. So the idea is to use both observations and high-resolution simulations simultaneously. What we're doing is we have built a dynamical core of a global model, and that same dynamical core can run at very high resolution, large eddy simulation resolution. And so this global model can telescope out high-resolution simulations when you need them, where you need them, when you decide to run them, to get the faithful simulations, say, of clouds or ocean turbulence and the like, in a limited area. And you can do this in one area, you can do it in two, and what we're currently doing is doing it in 20,000, which is a lot, but it's a lot less than the globe. But the key is, right now, when we develop parameterizations, we use a few data points from a few field campaigns, maybe half a dozen or a dozen at most. And that really limits our ability to calibrate, for example, cloud parameterizations. Most of these points are in subtropics or Caribbean tropics, use the same calibration in the Arctic, for example, and that obviously leads to problems. So here you can do high-resolution simulations anywhere driven by a global model, and at least it gives you better sampling in a computational sense. That gives you detailed data, and then you have observations that give you less detailed data, but real data for the globe. And what we want to do for climate modeling is, in a way, what has happened for weather forecasting decades ago. Weather forecasting got way better through data assimilation. you want to make climate modeling better through data assimilation, but the way you assimilate data is different, and importantly different from weather forecasting. In climate, the name of the game is make the processes better, get the energy balance right, and the like. So it's not about estimating the state of the atmosphere or the ocean, but it's about estimating processes in a model. And the way to do it is, in climate, you want to predict statistics, various mean fields, extreme values, and the like. So you use that as a target in data assimilation, that you write yourself an objective function that minimizes, for example, model biases, such as what I showed you for the cloud cover. But it can also minimize model data mismatches in any higher order statistic of the climate system. Could be covariances, that would mean avoiding emergent constraints, for example, or precipitation extremes is something you can directly target as a metric to get right. So that's different from estimating the state, and it's interestingly different in mathematical ways. I don't want to go into it. The bottom line is you have to compute these statistics from a climate model, which takes some time. You need a season or so to evaluate them. That makes it computationally more expensive than the, say, 24-hour or 12-hour weather forecast. But the advantage it has is that statistics are smoother than, say, states, and it results in much friendlier data assimilation problems than you have in weather forecasting. But computationally much harder because you have to run the model for longer. Now, we want to predict climate, so we want to predict something we haven't seen, and we need out-of-sample predictive capabilities. And our approach here was to use the known equations of motion, where we have them for the physical parts of the climate system, as far as you can, until you can't anymore, and then use data assimilation machine learning techniques to close the rest. So, for example, for turbulence cloud closures, we use equations of motion, we coarse grain them systematically, and in the end, you end up with terms that you need to estimate from data, entrainment rates, for example, and those we estimate from data. But we use the equations up to the point where an entrainment rate, say, appears, not throughout the equations before. And in everything, computational efficiency is really paramount. It's because for every time you evaluate your objective function, you need to compute a seasonal average of some climate statistic. You need to be able to do this with few evaluations of a climate model, few being about 1,000 is doable. That's what the typical climate modeling center uses in model tuning. But not 100,000 or 1,000,000, which is what typical Bayesian learning approaches would need. And we want to be able to quantify uncertainties, and there we use machine learning tools. So we use equations that, I'm not going to go through equations, we use equations. It's a process model for a closure. The point is, on the right-hand side, there's stuff appearing that in the end is things you learn from data, entrainment rate, detrainment rate, turbulent mixing lengths, and things like that. But up to that point, you use the equations where you have them. And building a whole or system model, atmosphere, ocean, biosphere components, biosphere is done by JPL, and everything is wrapped in some layer of data assimilation machine learning tools. So the idea is, in the end, that the entire platform will learn from the data, either high-resolution simulations at the bottom that you spin out, or observations that you have, space-based observations, floats, and the like. The key new thing is that this data assimilation machine learning layer wraps everything in one go, and that you learn about all components simultaneously, not piece by piece. It doesn't solve the compensating error problem necessarily, but at least after the fact, you will know where you have compensating errors. And let me just give you one quick, the question is, how do you do this learning? And let me just sketch this out. We have developed something we call calibrate, emulate, sample, and we, Andrew Stewart, as an applied mathematician, has been leading this, and some example from Emmett and Alfredo, a student and a postdoc. And I just want to give you one quick example of how it works, maybe that illustrates how it goes. So here's just an idealized GCM. It has a simple convection scheme, a Miller type convection scheme. It has two parameters in it, the relative humidity and a relaxation time scale. Just as one example of a parameterization, not a good parameterization, not what we actually use, just to illustrate the computational algorithms. And we use ensemble methods to estimate these parameters. So here we have an objective function that has relative humidity, mean precipitation, and precipitation extremes as terms that you minimize simultaneously. And you start with an ensemble of size 100, and this is in a 2D parameter space with a relative humidity and the relaxation time scale. The perfect model setting, we know the true values, it's 70% in 2 hours. And this ensemble of size 100, then it's a variant of common inversion that if you run this in 5 iterations or so, it converges to the true estimate, which is good. But what is bad is that the ensemble collapses almost to a point, meaning that the ensemble contains no information about uncertainty. You can prove that it essentially contains no information about uncertainty. The good news is you get a good parameter estimate in something like 500 climate model evaluations, and that's doable. The bad news is it doesn't give you uncertainty estimate. So to get the uncertainty after the fact, I think the nice idea we had was, well, you have 500 climate model runs in this case, and you can use them to learn something about the uncertainties. What we do is we train an emulator. Here I show you an example of the Gaussian process, but you could use, for example, the neural network that Mike mentioned for the purpose as well, and perhaps even better than Gaussian processes. Gaussian process is basically a regression on function space. This is just a cartoon illustration. You evaluate a function at these red points, and the Gaussian process interpolates between these points and gives you uncertainty of the function between the points, and then the uncertainty gets large, the shaded band, where you have no data on the function on the right or on the left. So the nice thing is it gives you a smooth interpolation with uncertainty estimate. And now we do this with this objective function, which in this example had 100 terms. And out comes this. So this is the same 2D parameter space. The black dots are the ensemble that has collapsed. It's just blown up now, so not quite a point, but a narrow cloud. And then color is what you get for the uncertainty in these parameters after we have trained the Gaussian process emulator along with the Kalman inversion algorithm, and then do Markov chain Monte Carlo with 500 evaluations on this emulator. So the key is that the emulator we can evaluate very rapidly. We can do it hundreds of thousands of times. And we use that for uncertainty quantification. And that works. It's computationally essentially for free after you've done the inversion. And that makes it fast and efficient. We call it calibrate, emulate, sample because you calibrate the model, common variance of common inversion. You emulate the model as you do so, and then you sample the emulator to get uncertainty. You can sample the model to get uncertainty in predictions. So you can do this with any number of model components, all model components jointly, and that's what we're working on. There's a lot of interesting work to be done. You have to develop these process models. We're at that. We're still working on the algorithms for uncertainty quantification, converting them to filtering algorithms. There's a lot of computational work that's ongoing, that's building this model that it runs fast. It is really all new code, which seems scary at first. We started in earnest 8 months ago, but in these 8 months, we have developed a new dynamical core that now works on GPUs and CPUs. And after it seemed scary at first, we're convinced it was the right thing to do because we already have a functioning core that has portable performance on all sorts of hardware architectures that I think would have been really hard to do if you use any existing model. So scary, yes, but it also, I think, in the end makes development faster to start over. So where we want to be in 5 years, we want to have a model that integrates data and nested high-resolution simulations in a learning environment. For the atmosphere alone, we want to have it within a year. We have these data simulation machine learning algorithms that are efficient enough for system models, and we still work on making them better. We want a model that has quantified uncertainties, which no model really has right now. And I hope in the end it will be a platform, really, a basis for an ecosystem of downstream applications, say for infrastructure planning, flood risk management, crop yield prediction, and the like, and the like. And we are at universities primarily, so education is important to us. What we have done at Caltech and MIT is establish crosslinks between computational science and earth science graduate programs. So we have students from either program working with us, the students coming from computer science, applied math, get certificates in environmental science or earth atmosphere planet science at MIT, and the other way around. The domain scientists get certificates and recognition for what they do in the computational and applied mathematics side. And the students seem excited about it, and I think it's important to train students to be broadly educated for the market they're facing. So thank you.
So regarding the uncertainty quantification, when you compute the uncertainty on the parameters or the parameterization, you use that to build stochastic parameterizations within the model, or it's more on the ensemble?
Yeah, you can do this with stochastic parameterizations, and that's something I think it makes sense from various perspectives. I mean, physically, when you get to the gray zone resolution, it makes sense to have stochastic terms. It makes sense to represent your ignorance, and we're experimenting with it. I don't think we haven't fully settled how to do this, but we have experimented with stochastic models, and they perform better in many ways, in some ways, than purely deterministic models.
So you obviously thought about it a lot, on how to teach people that this model will work 50 years from now. So you obviously have some idea of an experiment you won't run, but don't develop, that you will publish. Can you give us some insight of how the experiment will look like?
I mean, the proof ultimately is you have to make predictions and wait to see to what extent they're verified. And to start with shorter term predictions, they enter response into annual variability and see that you can do that well. That might give you some confidence that the longer term climate you can do well. What you can do, and the nice thing about having these nested high resolution simulations, you can run them in a different climate. So they give you some guard against overfitting, at least for the processes that you can compute that way. Say for the land biosphere, you can't do that. And there's no guarantee that in the end this will have a better prediction, but it's the usual thing in science. You'll have a model that has relatively few adjustable parameters, even compared to current GCMs. I mean, that's by for example, we have this unified parameterization for all the turbulence convection clouds that has far fewer parameterizations in current models. So if you have fewer parameters and a better simulation of the present climate, it's sort of the best hope you have that it will give you better predictive performance, but no guarantee, right? No guarantee that Newton's law would outperform Ptolemy's epicycles in predicting planetary motion. In fact, it didn't, which is interesting, but it was still the better model.
So maybe I missed this. So if you have this ESM now, right, that is going to be used to do more actionable science, things that you put the structure planning and collaboration. I guess I don't. So the ESM you're running in the end, that's producing your prediction, that's still going to be limited by conventional limitations such as like grid resolution. And these impacts, right, these applications are still at weather scale, right? Oftentimes, right, the impact of infrastructure or flood risk is going to still be at weather scales that are under resolved even at 100 kilometers, even at 25 kilometers. So I guess I'm a little unsure how you recognize.
Yeah. Yeah, I mean, you have a global model that has a limited resolution, that's true. So you have a sort of computationally intensive training phase, and then you run this model like any other model. However, you still have this capability of an high resolution simulation. So if you want to know something about impacts over Long Beach, California, you can still have locally extremely high resolution simulations over the area here and get high resolution predictions of extreme precipitation driven by the global model.
But does that, so I mean, you can do that to some extent with current generations of models. You can run a, most of them have at least grid refinement.
Yeah.
And so what is the new aspect here? The new aspect is that the underlying model is a better developed model, so you can trust the fact that, because there's always issues with you when you have regional refinement of whether, what you're refining in that region and the climate that comes out of that region is consistent, and how does that work its way up to the large scale climate, right, the application of that. So is there...
I think there are at least two crucial new pieces. A is there's no model that uses data to A, calibrate it, and B, quantify its uncertainties, right? So what you have here throughout, you have an end-to-end uncertainty quantification pipeline. You have the uncertainty in the global model. You can propagate that through into any high resolution simulations you do. So you'll have a model that I hope in the end will give you a better climate and hopefully better predictions, but there's a hope in that. But then B, you can quantify uncertainties throughout, and you can get at those uncertainties in your local predictions.
I think it's kind of linked to the previous question. So to do actionable science, right, and to to do future predictions, as you're saying, versus projections. It requires actually, I would argue that CMIP and the way we typically do projections isn't actually built up to necessarily risk assessment per se, because these are projections of a world that based upon assumptions that are never going to happen, right? And so the question is that still something, is that built maybe somewhat into your uncertainty quantification, or is that a different application that could be?
No, and okay, when I say prediction, I didn't want to make too fine a point, prediction versus projection here. I mean, we're not going to model human systems. So the human uncertainty is going to be there, and it's not something they're going to be able to quantify. However, I think what the people funding us want is information on a decadal timescale, 30 years or so, where the human aspects are relatively small. And so that's probably not the major part of the uncertainty. And maybe let me say this more broadly. I don't think this is sort of the be-all, end-all and tells you everything about uncertainties, but it's a step towards doing better than we have. And I think that's what I want to do.
So I am always a fan of like a new approach, but I have a question. What motivated you to develop a new model instead of taking advantage of current like NCAR model, GCL model, and I'm just very curious. And I also wonder whether there's collaborative your efforts and like say yes.
Yeah, so the last question is really easy. Absolutely. This is very much an open development, an open project. We love to work with others, and we love to grow the group of people contributing, we love to work with NCAR and everything else. So that's easy. Now, why a new model? Had you asked me 3 years ago, do you want to develop a new model? I would have thought it's crazy. And there was a gradual erosion of thinking it's crazy. It wasn't the morning I woke up and this is what we should do. And the gradual erosion had concrete reasons. And too long to go into all of them right now, but let's just say take the die-core and cloud internal prioritization as 2 examples. The dynamical core, so we all have to compute on architectures that we don't know what they really will be a few years from now. And GPUs is sort of the latest thing, but it's already yesterday's thing in some ways. There's something coming after GPUs. So there'll be heterogeneous architectures with accelerators that we need to learn how to compute on. And no one is really ready for it yet, right? And so then we wanted a global model that can spin out high-resolution simulations from the same core. And what I've learned from working on stratocumulus clouds especially is that high-order numerics is very important to do as well. So you wanted a scalable model that runs on GPUs and has high-order numerics, and you look around, there's none that can do it. And so that's part of where new die-core development came in. But gradually it emerged as, well, maybe this is an opportunity. You can develop a core and new software, modern ideas of software development using an all-new language, Julia, which has been great for us in accelerating development. There's no way we could have developed an all-new die-core in a few months that it has portable performance in any other language. And it had advantages in the end. For the prioritization part, it was a similar story that, there was a strong sense we need to unify these disparate prioritizations, and you could take pieces and try to stitch them together, but in the end, it was easier to rethink it over how to develop it from scratch in a unified way, using all the insight we have gained over the last few decades about cloud processes and turbulence processes. All of that flows into that, right? And that's part of what's appealing to me. I mean, it's fundamental science in the end, and it builds on decades of work. It's not throwing it out and saying, we stick a neural network there, but it's building on it, yet redeveloping pieces. In some way, I mean, asking a question, what would Akio Arakawa have done if he would develop a convection prioritization now with the computational capabilities and observing capabilities we have now? What he did was fantastic for the 70s, but maybe not what he would do now. Asking those questions.
Great, thank you. Well, first of all, thanks to the CLIVAR Organizing Committee for inviting me to present on our work on deep learning. Unfortunately, I picked up a stomach bug this weekend and can't travel, but I'm glad that I can still present remotely despite some of the AV issues. So this is work that we've been doing at Lawrence Berkeley Lab in collaboration with several others. This is with Prabhat here at the Data Analytics and Services Group at NERSC, several grad students and postdocs at UC Berkeley, folks at the Climate Department, Travis O'Brien, Michael Weiner, and Bill Collins here also at the lab, but also with several others that have visited either as interns or collaborations that we've developed over the last few years, including Ben Toms, who works with Libby at CSU, some folks from Lawrence Livermore, from Stanford and Caltech, and also Microsoft and Google and NVIDIA. So a long list of people that have contributed to this work. And I think I'll just dive in. Next slide, please. So we've seen some talks on using machine learning and data analytics and data science in general for various different applications. What one would call climate analytics is sort of one broad category. Libby talked about hypothesis generation in the last talk, and then earlier Tapio was talking about using data science and machine learning for sort of integrated Earth system modeling. In this talk, I'd like to focus on the analytics aspect, and then maybe mention briefly about some of the work that we're doing also for climate modeling. So the key challenge here is to characterize extreme weather in a changing climate. This is water vapor fields from the 25-kilometer CAM 5.1 simulations that Michael Weiner ran a couple of years ago. Clearly, we see these highly organized structures in the atmosphere, and some of them we do recognize as hurricanes and atmospheric rivers and extratropical cyclones and several other events. But there's a wealth of patterns that exist here that are important for impacts as well as for understanding how the system behaves. And we'd like to be able to characterize these patterns, but the big challenge is how do you first identify these patterns and how do you do them reliably across very large data sets? So moving on to the next slide. So the same problem, of course, exists in doing this on satellite observations as well. On the top, we see this sort of unusual series of hurricanes in the Atlantic, and then the bottom is the classic atmospheric river events that bring over 50% of the rainfall to California. So being able to detect these events reliably in large data sets is where deep learning can be used. Next slide, please. So this is probably maybe very clear to the audience here, but I just wanted to point out some of the recent extreme events and the impacts and why this is actually a critical problem. This is Mono Lake at the end of the drought in 2016 in California. It was completely dried up, which was the first time it was happening in several decades. And the next slide, please. Sorry, can we move to the next slide? Thank you. This is the Oroville Dam crisis after a large atmospheric river event in 2017, which led to severe impacts both for the environment and for society, and it was very expensive. And these types of events are becoming increasingly frequent, and also some of them are more intense. So we'd like to be able to characterize how extremes are changing as the globe warms. And the next slide. And this is, of course, the wildfires from last year in California, which were devastating and is likely to be, again, increasingly frequent as we warm the globe. So moving on. So I'd like to basically highlight some of the results that we have in deep learning for pattern recognition, classification, localization, and segmentation. I'll define these terms shortly. For tropical cyclones, atmospheric rivers, and weather fronts, then give a very quick highlight of some work that Ben Toms did here last summer at NERSC on deep learning for detecting the MJO, and then ClimateNet, which is an initiative that we've launched about a year ago for essentially developing a community-sourced large data set for training deep learning models, and finally conclude with some challenges and opportunities, some of which have already been talked about. Next. So Libby showed us this example of sort of a vanilla neural network. You have a dog and a cat, and you're trying to do classification. So that's It's already a concept that is familiar to many of you. A similar sort of analogous concept would be detecting if an image has a hurricane or some other extreme weather events. Kind of the next level is to localize that particular object. So in the second column, you see a cat, but then a box around it. And that basically is sort of the classification plus regression problem, where you're also trying to find the exact locations of these events. Similarly, we could do that for hurricanes. The next level is object detection, which is doing the classification and localization for multiple classes of events, some of which might be overlapping. So you have dogs, ducks, cats, etc. Similarly, we have hurricanes, atmospheric rivers, extratropical cyclones, other patterns of importance, and all of those can be detected simultaneously using deep learning. And finally, sort of the holy grail of computer vision is segmentation, which is pixel-wise classification. So given an image, classifying every single pixel of that image into different classes. Similarly, for climate, that would be drawing these very tight boundaries around events that have complicated shapes. But of course, there's some key differences between sort of computer vision and deep learning as it exists today and the challenges of scientific data. First of all, we have multiple variables in climate science, often tens of variables, and RGB is just 3 channels, so that's a big change. The scales that we're dealing with here for these patterns are likely very different from the ones from natural images. So we have a wide range of spatial and temporal scales. So detecting these patterns is not just sort of off the shelf black box deep learning models. We would have to retrain them for these patterns. The data is double precision floating point often in science, and not the case in images. And finally, underlying statistics of these events are likely quite different from natural images as well. So there's a lot of work to be done to make these methods actually useful for science and not just sort of directly use the ones that exist out there in the industry. So next slide, please. This is examples of pattern detection that we've used various different machine learning methods, so logistic regression, k-nearest neighbors, support vector machines, random forest, and of course deep neural networks. We see that across the board for patterns that are highly organized and have very strong features, most machine learning models work fairly well. So tropical cyclones, we trained on Cat 4 and Cat 5 hurricanes, and most of these models do a good job of classifying these patterns. But as we get to more complex patterns like atmospheric rivers and weather fronts, deep neural networks tend to perform better than some of the other methods. But this is just to sort of give an example of how deep learning has been successful in pattern classification of a few different types of weather patterns. And this is now a couple of years old, presented at Europe's in 2016. Next slide, please. So the next level of tasks is semi-supervised detection, which is very relevant for scientific data, especially because we don't have labels for most patterns. Some of them are completely unlabeled, some of them have few labels. So trying to create a unified architecture for all weather patterns and being able to detect them, but also to discover new patterns that exist in the data that we haven't actually labeled or given a name to is where semi-supervised detection becomes useful. Next slide, please. So this is the image that Libby showed in her introduction. This is where we used a semi-supervised detection system for detecting tropical cyclones, extratropical cyclones, and atmospheric rivers. In green is the ground truth data, which comes from essentially heuristics that have been developed over the decades for detecting these patterns. So they're fairly basic sort of threshold conditions on different physical variables, and those are the ones that we currently use today for object detection in weather and climate. So those were used for training these neural networks, and then the predictions are in red. What we see is that the neural networks do a reasonably good job of detecting the location, but they find it really hard to get the size of these events right. And one of the reasons for that is because in physical fields, things are continuous. So gradients exist and things gradually dissipate. We don't have sharp boundaries like a dog sitting in front of a cat or a cat sitting in front of a bicycle, which are very sharp changes. So that's something to keep in mind when we use these methods for estimating the sizes of events. And of course, on the top right, we see the extratropical cyclone was not detected by the neural network, and that's because, again, the features here are much more mild, so the signal to noise ratio is much lower for these features, and hence the networks find it hard to detect these. So this was at NeurIPS in 2017, so again, a couple of years ago. Next slide, please. And finally, this is sort of the latest and greatest that's come out of the group in terms of climate analytics, and this was the Gordon Bell Prize winner last year in 2018. For those of you that are not aware, the Gordon Bell Prize is awarded to, it's a computer science award for scaling systems out to very large scale and with various different criteria. So here, Prabhat and the group had this sort of marathon effort towards taking a large segmentation system, which was designed a couple of years ago, and splitting it out onto all of the GPUs on Summit. So that was about 27,000 GPUs. And this is just a snapshot of the results. Here we see in blue the atmospheric river events, and in red tropical cyclones. And of course, the climate scientists in the room would look at this and say, "Hey, this doesn't look quite right." And I think that's a very pertinent comment or sort of opinion to have about these results. You can see that some of these structures are broken up into two pieces or more at the bottom. In the southern hemisphere, east of South America, we see the atmospheric river is sort of broken up into two, and we see tropical cyclones with lots of other sort of dots around them. So there's clearly a lot of work to be done in improving the quality of these results, but what we've shown is that these are scalable onto very large systems. And that sort of leads me to one of the next challenges. Next slide, please. Sorry, before I get to the challenge, I'll point out some of the recent results also for events of sort of multi-scale behavior. So the MJO, of course, many of you are aware, is a very important phenomenon in the tropics, and also has far-reaching impacts because it has predictability for other types of events, including atmospheric rivers. So trying to detect the MJO was something that we hadn't done before with deep learning, and we weren't sure if detecting a large multi-scale event like that would be possible. But Ben-Tom showed that you can classify the phase of the MJO very accurately with neural networks. But most interestingly, you can do some clever permutation techniques and other stats statistical techniques to essentially tease out specific behaviors and also generate hypotheses, as Libby showed in the last talk. And here is an example of one particular way to generate a hypothesis. You can basically backpropagate noise through the network to detect every single definition of what the MJO is according to the deep neural network. So on the right is the deep learning definition of the MJO. On the left is the original definition of the MJO as defined by MJO scientists using the case of this. So there's a bit of background. Can someone, or is that coming from the room itself? Never mind. Well, so what we see here is that the deep learning model does detect the MJO definitions as we understand them, but there's also a lot of other features that the deep learning model uses to define the MJO. And now this is a way to essentially validate that the deep learning model is actually learning something that's meaningful and it's not picking up spurious signals. So that's satisfying, but more interestingly, the deep learning method might be able to provide hypotheses for how the MJO behaves or how its signature in various different variables change, which variables are most important, and so on. So that was an interesting piece of work that came out of last summer with Ben-Tom's, and this is on arXiv, and we're sort of revising it before we submit it to a journal. Next slide, please. So this sort of connects to the point that I made about the exascale project, where even though we were able to scale out these very advanced architectures on 27,000 GPUs, the quality of the actual science results were limited by essentially the quality of the training data. So a lot of deep learning depends on the quality of the training data, especially in supervised mode. And one of the challenges of weather and climate science is that we do not have high quality labeled data in large amounts, and that's essential for improving the performance of these deep learning models. So as a sort of consequence of that limitation, we've launched this large project called ClimateNet, which we talked about at AGU last year and then at ICML this summer. And the goal of the project is to create this large database which stores features about various different types of events coming from either observational data or climate model output. And we've developed this tool called Climate Contours, which you can go online right now and use it. The link to the website is there that describes the project, and then within that is a link to this tool. The tool is basically a labeling tool, so you can go and load in an image and label a tropical cyclone or an atmospheric river. As you can see on the bottom right, it's just a snapshot of what that looks like. So we have these different polygons that we can use to draw boundaries around these events. And then once we're satisfied with that, we say next, and all of these get saved as masks, basically. And you can imagine that if we have hundreds of people or at least tens of people starting to do this, we can start to generate hundreds of labels. And eventually, once we expand this project out, we can create a database of several thousands of labels, which would then start to help develop these deep learning models that are of much higher quality. So that's the vision for this project. I'm very actively looking for collaborators that can help me with expanding this project out, adding new features, changing the tool for other types of images or other types of data, and then finally developing the deep learning models that will work off of this database. So please let me know if you're interested. The key here is that we're trying to avoid the heuristics that have been used so far because there's large uncertainties. Some of you are aware of the ArcMap project, which essentially quantifies the range of different models that are used for tracking atmospheric rivers. And from some of the recent results, we see that things like precip and other variables can be off by a factor of 10 across these different methods. And there's large uncertainties in the ways in which these tracking algorithms work. So if we can sort of circumvent that and directly go to the experts who can help us label these events, that might be a big step forward. Next, please.
Karthik, you have 2 minutes left.
Okay, great, thank you. So I just want to quickly highlight some work on physics-informed deep learning. This is just a one-slide snapshot of this. As was mentioned in the previous talks, developing reliable and robust deep learning models require them to basically obey the laws of nature. We know a lot about the systems that we study. There's a lot of known physics and domain knowledge and observational data. So how do we incorporate this into deep learning is a big question. We've made a small step in that direction using something called generative adversarial networks, GANs, which is all the rage today in deep learning. Almost every month there's a new type of GAN coming out, but the step that we've taken here is to try to incorporate constraints from the spatial temporal structure of the training data. This is for Rayleigh-Bénard convection, which is an idealized form of atmospheric convection. And this is work done by Jinlong and others, where we trained a generative adversarial network to emulate the physics of Rayleigh-Bénard convection, and then test it on the right using various different metrics. Here we show the energy spectrum. So the kinetic energy spectra are much better for the GAN that is constrained by the physics of this process as against an unconstrained GAN. If you'd like to learn more about this, please check out the paper on arXiv, and I'd be happy to chat about it some more. Next slide, please. So I just want to conclude with some of the challenges and opportunities. Some of these were already highlighted in previous talks, but hopefully this will sort of synthesize all of that. So one of the big challenges is, of course, climate data is complex. We have multi-dimensional data, multi-channel. Some of the data might be very dense and some very sparse. It's multi-scale, so we have a range of scales, and we'd also like to be able to capture the spatial and temporal coherence that exists in these events. Hyperparameter optimization, which is something that's needed in deep learning, which is how do you tune these different layers and filters and weights and and so on, and that remains a bit of a black art. And of course, that's not the job of a climate scientist to work on, but that's something that the field would benefit from. Performance and scaling is a challenge, especially with the kinds of data sets that we deal with in climate science. Current networks take days to train on tens of gigabytes. We already have petabytes of data, so scaling these things out is very critical. And finally, as I mentioned, we don't have high quality, reliable label data, so we need to create these sort of campaigns and self-organize to generate the required high quality training data for these deep learning models. Next slide, please. So I'll just conclude with some long-term challenges. There's limits on the theory. We don't understand the limits of supervised, unsupervised, and semi-supervised learning. GANs are promising, but they're unstable and hard to train. Interpretability and explainability is a big challenge. We need to be able to understand what these models are learning, and Libby talked about some of the work that they've been doing on that. And then explainability is also, why do these models do the things that they do? And then finally, being able to incorporate the domain science principles that we already have into these models. UQ is a big challenge as well, and Tapio mentioned a little bit about that. And then finally, we don't have a formal protocol for applying deep learning. I love the cartoon that Libby showed. It's basically, throw a bunch of data, throw a bunch of compute, get some algorithms, and keep churning, and you finally get something out. But we really need to develop a systematic framework for applying these models, just as the applied mathematicians have done with solving PDEs, for example, discretizing, having stability criteria, conditions, and so on. So that's long-term work. And I'll conclude with the next slide, please. So just a little bit of advertising at the upcoming AGU, along with some others from CSU, including Ben Toms, we're co-organizing a session on incorporating physics and domain knowledge to improve the interpretability, explainability, reliability, and generalization of machine learning models. Please do attend that session if you can. I'm also conducting a tutorial on machine learning and deep learning for the environmental and geosciences. The date is to be decided, but it'll be a day-long tutorial, hopefully the weekend before, or maybe one of the days of the week. And then finally, we're also co-organizing with several others a machine learning for the physical sciences workshop at the upcoming NeurIPS conference. And with that, I'll stop and take any questions. Thank you.
Thanks, Karthik. Any questions for Karthik? Tony?
Thanks, Karthik. This is Tony Lee. Could you go back to the MJO example? So the plot on the left is the original MJO definition. I suppose that's the Wheeler and Hendon index, multivariate UF. And the right-hand side is a deep learning approach.
That's right.
Okay. So it strikes me that the deep learning definition have the MJO pattern going all the way across the tropical Pacific. And I thought that MJO is known to decay after going through the Western Pacific, and they don't really have much of a signal in the Eastern Equatorial Pacific. So could you comment on that, or is this revising the understanding of the MJO pattern?
Yeah, so I might redirect that question to experts in the room that actually work on the MJO. I'm not an expert myself on the MJO, but I think this is an example of basically a way to generate hypotheses. So if we do think that the deep learning model is learning something useful, then maybe this is one way of framing this is that maybe there's other behaviors about the MJO that we don't understand, and we might have to sort of frame hypotheses on whether the MJO exists across the tropical Pacific. Is there other patterns that are associated with the MJO that don't exist in the standard definitions of the MJO, but are actually important for the dynamics of the MJO and so on. So I don't know if Libby has any comments on this or anybody else.
Thank you.
Samson?
I'm not that familiar with the work, but one thing that could be happening is the machine learning could be detecting dynamical signals like Kelvin waves, for example, that could propagate faster. So you see the blue things extend further to the central Pacific and so on. So that could be part of divergent signals just without the OLR and precipitation. So the deep learning may be learning more than what we typically think of as MJO.
So just a follow-up comment. I think what Libby said really resonated with me. Look into the toolbox, try not to call it black box, and find out why we get that pattern, or why we get that prediction. And I think that's the most rewarding. So like explaining why would there be a difference between the traditional multivariate EOF and the machine learning approach. Yeah. And I hope that this discussion and the working group will help bring that kind of understanding into a newer level among the cognitive scientists.
Charlotte, did you want
Thank you.
This might contradict what Samson just said, but just in looking at this, to me, it appears that the deep learning definition is really picking up on the cloud signatures. So the traditional Wheeler-Hendon definition, we know is heavily weighted towards the circulation anomalies, which can persist much longer than the convection itself. So just the fact that the OLR anomalies are larger in the deep learning definition, also looking at some of the structure of the anomalies, say in phase 4, just makes me think that it's picking up more on the convection, whereas the RMM indices are pretty heavily weighted to the global scale circulation anomalies.
Right. So if that's the case, do we call the right-hand side still MJO? Because that's a huge implication to the MJO community and S2S for MJO prediction, right? So, the Wheeler-Hendon index is looking at the zonal wind and other variables, lower level wind, higher level wind. And if this is picking up at more of a convection, and does that hold the key to some observable that help MJO prediction, for example?
A quick comment on that. I do think it's, at least in my brain, the way I think about this is there are two separate questions. One is, should we, is this now the MJO? That's I don't want to be in the room for that question, I don't think. But also, what is useful for prediction? And actually, I'll show some work later today in the sub-panel saying what aspect of the MJO is leading to predictability in rainfall, say along the US West Coast. And using some of the methods I discussed, we can start to look for the dynamics that are happening that say this is the part of that whole tropical signal that's actually the important piece. And the hope is, and we think we can do this, is link it back to our dynamical equations of what's actually going on with the convection, exciting the waves that then propagate into mid-latitude. So I think they're slightly separate in terms of what's useful for prediction and what is sort of this dynamical MJO. But anyway.
Thanks, Libby.
Thank you.
I had a related question, Karthik. So is there a uncertainty estimate on this deep learning definition of MJO or other patterns?
Yeah, so we already showed that in this image, but you can do that. So the way we obtain the deep learning definition is we backpropagate white noise through the entire network and we maximize the one particular class. So you have to do this for every separate class. And then in that entire backpropagation process and then converging onto that particular definition, you can do that multiple times and you'll get slightly different definitions each time. So you can create an ensemble of definitions and then create an uncertainty around that.
Great. So that might also indicate where we can trust the deep learning definition more.
Exactly, yeah. Yep.